Right, okay, we're going to carry on with the electric. Where are we? Oh, that helps. Right, state what is meant by the term electric current. So one marker. Current is the rate of flow of charge. That's it. So you've got DC, direct current. Direct current does not go in that direction and that direction, up and down, right? It's like it's from a cell or a battery. Remember, cell is single, so it looks like this. Plus and minus, but they've drawn it like this and they've labeled it DC, power supply. So just be aware of that. Right, you've got a component here which is a resistor. You've got a fuse because it's got a line through it. And you've got a light emitting diode. It emits, it gives out light. Give a reason why an LED is included in the circuit. It's to show you that it's working. This is to show the fuse is still working. So I should have read this. The diagram shows an electric circuit used to test a fuse. To show that this is still working, and this wire here, right, has not melted and broken the circuit, so it becomes an open circuit. The LED, as it's emitting light, you know it's working. Right, add another component in the circuit to measure the current of the fuse. The current in the fuse. So all we do is we add you can add it here, just an ammeter, or even anywhere. You could add it anywhere, to be honest with you. But because they focus your mind on the fuse, just stick it here. Just get rid of that, get rid of that, get rid of all that. That's just causing a bit of, right, just stick it there. Right, as long as it's in series. Let me highlight that again. Ammeters are in series, in the same line. Voltmeters are parallel. Just remember that. It's good to know that. Right, okay, we've done that. Right, here's another diagram. Diagram shows different electric circuits containing 3 different lamps. It shows a different electric circuit showing 3 different lamps. So what happens here, look, try to follow this. The current comes down here and then it splits up down here. So you end up with 0.4 going down here. And then when it comes down here, it splits up into. So we now know 0.3 has gone down here. So 0.1 must go down there. So remember, this is what it is as current comes in and it splits up like this. So just if that's I1, that's I2, and that's I3. So the current coming in equals the current going out. So I can say I1 is equal to I2 plus I3. There you go. Calculate the current I1. Calculate the current I1. Okay, yeah, we did that. it's a 1 marker, it's going to be 0.1. So we did 0.6 minus 0.2 minus 0.3. State the current I2. Can you see? Oh, okay, I2 is up here. So what's going to happen? Let me get rid of all this. So all the current, so 0.2 is coming in, 0.1 is going here, 0.3 is coming up here, so 0.3 comes up here, 0.1 comes up here, so by the time it gets here it becomes 0.4, 0.2 coming in here, 0.4 coming up here, so it becomes 0.6. Right, so that becomes 0.6. So the current running through will be the same. Explain which lamp is the brightest. It's the lamp 0.2, 0. It'll be lamp 3 because it's got the highest current going through it. So look here, that's got the highest current going through it. This has only got 0.1. Let me use another color. So this has got 0.3. Did I just do that? Yeah, 0.3. This is 0.1 and this is 0.2. The higher the current, the brighter the lamp. So it will be, we have to explain why. So it's a 3 marker. So lamp 3 because current is greatest. Is greatest, the highest. Right, okay. We know power equals current times voltage. And because they are in parallel, look, it's a difficult one, so just understand this. This component and this component are in series, right? This component and this component are parallel. So if you see something like this, like a ladder, you know, you've got a ladder here, you've got steps of a ladder. They are parallel. The voltage is the same. The current may be different. With this one, this is called a series circuit. The current is same, but the voltage may be different. Just try to remember this. Just keep repeating it. It'll go in. So we're saying power equals current times voltage. The voltage is the same because it's parallel. So so the current is big times the voltage, which is the same. So the bigger the current, the more power, the brighter it'll be. That's it. It's a 3 marker, so let me right, because the current is the greatest, because power equals current times voltage. See, they've used PIV here now, PIV, and we know that the voltage is the same. Why? Because in this, the components are parallel. The voltage is the same and current is the largest out of the 3. Done. Right, that's that done. Right, okay, we're now looking at question number 8. A student moves a wire. Okay, no wrong with that. A student moves a wire between the poles of a strong magnet and uses the ammeter to measure the induced current. Determine the current reading shown by the ammeter. So we just need to read this. It's 2.4, yeah, 2.8. You just got to learn to read the scales here. So between 2 and 4, I've got 2, 3, 4. Right, okay, so 2.4, 2.8, 3.2, 3.6, 4.0. Predict the value for the current if the movement of the wire was repeated with the poles of the magnet reversed. It would be down here. It would be down here, so it would be minus 2.8. Predict the value if the current, the wires move faster. So if you move it faster, you'd get a larger reading because you're cutting the magnetic field lines at a quicker rate. So it would be larger. Nope. So it would be a larger reading than 2.8 milliamps. There you go. Right, D. Shows photograph 3 shows part of the ammeter after students adjusted the ammeter in error. Ooh, okay. The needle on the ammeter does not point to 0. There is no current. Which of these factors has been decreased by the student's adjustment? Ooh. Right, the accuracy, okay. Not precision, it's not using the smaller, not resolution, and not reliability. It's the accuracy. So it will always be this much out. Okay. Suggest how the student could correct the readings taken from this due to this error without adjusting that. I mean, you just subtract it. So you just you add or subtract the 0.4 by the looks of it. 0.4 from the final measurement. That's it. It's a 1 mark. It's not. Okay. Right, we'll call it quits there. I think that's a good point to stop that.